Welcome back to part 2 of lecture 16. So in this part 2, first we'll briefly summarize all the different ways that we learn to count outcomes of problems. And then after that, we'll solve a couple of example problems. So let's get started with the summary. So in lecture 15 last week, we introduced a number of basic rules for counting. So we introduced the rule of products, which tells us that if we can select values individually, then we have to multiply their counts. Then rule of sums, so we can split the problem into disjoint sets. We can add their counts to get the final count. Then rule of sums with overlap. If the split into disjoint sets, if the split is not into disjoint sets, so meaning there is an overlap between sets, we must subtract the count of the overlap. And finally, we introduce the rule of complements, which tells us that the count of objects with a certain property is the same as the count of objects without the property subtracted from the universe count. So we saw, for example, the rule of complements in the dice problem from part 1 of this lecture. Then we also introduced formulas for computing counts of certain structures. So the number of ordered list of length r chosen from n elements is n to the power of r. Permutation of length r chosen from n elements is denoted as p n comma r, which is equal to n factorial divided by n minus r factorial. As a special case, if r is equal to n, then the number of permutations is equal just to n factorial. Okay. We also introduced combinations in lecture 15. And remember, we derived the expression for combinations by relying on counting with equivalence classes that leads us to dividing by r factorial the number of permutations when the order does not matter. And so if we leverage this, then the number of r element subsets chosen from an element set is denoted as c of n comma r, and that is equal to the number of permutations divided by r factorial, which is equal to this expression. So don't forget that you have to divide it by r factorial. So that can be a common mistake if you forget this. And finally, in part 1 of this lecture 16, we showed how to use binary sequences to count unordered lists with repetition. So the number of binary sequences with r ones and n minus r zeros is choose r of n, which is the same as choose n minus r of n. And then we also showed that the following are equivalent and have the same answer, c of r plus n minus 1 comma r. So the number of unordered list repetitions of length r from the set of size n, number of non-negative integer solutions to this equation, number of binary sequences of length r plus n minus 1 with exactly r zeros, and number of bags of r items with n item types. And we leverage these equivalences in the part 1 to calculate solutions to a couple of example problems. Okay, so now that we are done reviewing what we covered in lecture 15 and first part of lecture 16, let's use this to solve a couple of example problems. First, a sequence example. So the problem is to calculate how many 10-letter sequences from the set of letters MAT contain exactly 3 instances of the letter M. So you should be able to calculate this on your own. And so I won't keep repeating this, but I urge you that now you pause the video and try to derive this on your own, and then check your solution against my solution that I'll show on the next slide. So what is the algorithm here? So we first place the m's into 3 of these 10 slots. So this is the same as choosing 3 element subset from this set of 10 elements from 1 to 10, which we know how to calculate. So that's C of 10, 3. So again, I illustrated this in part 1. So we have these 10 slots, 3, 4, 5, 6, 7, 8, 9, 10. And first we are choosing 3 places where we are going to put m's. I should say we choose this one, maybe this one, and this one. So that's choose 3 out of 10. Now we are going to put either A or T into each of the 7 remaining slots. So we are going to fill in these 7 remaining slots with A or T. So this is actually the same as building an ordered list of length 7 from set AT. We can disregard m's, right? Or you can just fill in the slots. And that amounts to 2 to the power of 7. We have 2 letters and 7 slots. So the answer then includes using the rule of products, and it's choose 10, 3 times 2 to the power of 7, which is equal to this number, 15,360. Okay, let's look at another similar sequence example that builds on top of this one. So how many of those 10 letter sequences contain exactly 4 A's? So we have 3 M's and 4 A's. Again, try to do this on your own, and let me solve it on the next slide for you. So what is now the algorithm? Well, the same as before. We first place 3 M's. Let's choose 3 out of 10. Now we have exactly 4 A's, so we can place these 4 A's. So that's choose 4 out of 7 remaining slots. And finally, we place T's in the remaining 3 slots. Clearly, this evaluates to 1. And then the answer is the product of these 3. So we are using the rule of products. And when you calculate it, you get 4,200. Okay. So let's move along. Let's look at another example. So this one is about word arrangements. So the question is to compute how many distinguisher arrangements of the letters in Mississippi are there. So try to do it on your own, and after we're done, take a look at my solution, which goes as this. So this is the same as building an ordered list of length 11, because there is 11 letters in Mississippi from the set including letters M, I, S, and P, with the restriction that there could be only 1 M, 4 I's, 4 S's, and 2 P's. So this problem is equivalent to the one we just solved. And so what is the algorithm now? The same as before. We place the 1 M. Let's choose 1 out of 11. Place the 4 I's. Now we are choosing 4 out of 10 because we used up 1 spot to put this M. Now we're placing 4 S's. So we're choosing 4 out of 6 because we used up 1 for M and 4 for I's. And finally, we place the 2 P's. And we have to multiply this using rule of products, and this is the final number we get. As a side question, does it matter what order our algorithm uses? Um, short answer is no, it doesn't matter. Clearly, it doesn't matter in which order we are going to place these letters. And in fact, I suggest that at home, you try to calculate a few different orders and see if you get the same number. And you should always get the same number, this one. So do that exercise at home. Let's now look at the following problem that involves baseball. So we are tracking a baseball player by writing down their performance in 10 successive plate appearances, meaning we are looking at an order list of length 10. For each plate appearance, we are writing down an H for hit, S for strikeout, B for based on balls, and O for other. Know that I also am pretty clueless about the rules of baseball, but you don't need to know how to play baseball to be able to solve this. You can abstract away from the game itself, and then we are just looking at sequences of these letters H, S, B, and O of length 10. So this problem is in fact quite similar to the problems we just solved in the last couple of slides. So how many results total are possible? So we are looking at order list of like 10 out of these 4 elements with repetition, because, for example, all 10 can be hits. And so we calculate this as 4 to the power of 10. So we're drawing from 4 elements, and the length is 10. Okay? Now the question is, out of all possible results, how many have exactly 3 H's? We solved a very similar problem to this. So we need exactly 3 H's. So first we are going to place these 3 H's. So we are going to choose 3 locations out of 10. So we place 3 H's, and then we have 7 spots where we can have any sequence of S, B, and O. So we have 3 options and 7 leftover spots. So that's the solution to this one. Now the final one, out of all possible results, how many have exactly 4 H's, exactly 1 S, exactly 2 B's, and exactly 3 O's? Again, this problem is identical to the problem where we were calculating sequences of letters. So we have exactly 4 H's, so let's place them first. So we are going to choose 4 out of 10 spots times we have exactly 1 S, so we are going to choose 1 out of 6 leftover spots. Then we have exactly 2 B's, so we are going to choose 2 out of 5. And finally, oh, I'm missing C's. Choose. And finally, we are going to choose 3 out of 3 for O's. I'm not going to calculate this here. You're more than welcome to calculate at home. But these are solutions to this practice problem. So make sure to understand this. Okay. So the final problem we're going to solve in this part 2 goes as follows. How many different bags of produce can we bring back from the store, assuming it sells apples, bananas, oranges, and peaches? And we buy at least one of each type of fruit, and altogether we purchase 15 pieces of fruit. So there are a couple of different ways to solve this problem and how to go about it. I like to relate it to that equation involving integers. So this problem is equivalent to the equation, to the number of solutions to the equation x1 plus x2 plus x3 plus x4 is equal to 15, where each of these x's is greater than 0, because we need at least one of each type of fruit. So whenever you see a problem like this, you have to be really careful. The question you always have to determine is, can we have 0 of certain types of fruit in the bag? And so in this case, no, we need to have at least one. And so we did this in part 1. So this equation, where x has to be greater than 0, is equivalent to the following equation: x1 prime plus x2 prime plus x3 prime plus x4 prime is equal to 11, where xi prime is greater than or equal to 0. And we know how to calculate the number of solutions for this equation. Is equal to C of R plus N minus 1, comma R, where R is equal to 11, this is R, and N is the number of these variables, so N is equal to 4. So that is then equal to C of R 11 plus 4 minus 1, comma 11, and that is equal to C of 11 plus 14, comma 11. So this is the solution to this problem. Again, try to calculate the actual number at home. It shouldn't be too hard. And with this, we conclude part 2 of this 16th lecture, and we also conclude our lectures on combinatorics. So I'll see you on Tuesday during the recitation sessions. Bye, everyone.